And Drew, if you want to get started with some of the MetPy content. Drew is a software engineer at Unidata and works on MetPy, which is an amazing open source resource within the Python stack to work with meteorological data. So, Drew, the floor is yours.
Wonderful. Thank you, Max. Let me know if for some reason you can't hear me, but let me try sharing my screen. I've yet to do that on this computer. Let's see. Jupyter Lab. Okay. Is that coming through pretty clear, Max?
Looks great.
Okay. If it's too cramped or if I need to zoom in to make it any more legible, please make a note in the chat. Thanks again, Max, for the introduction. You covered much of it there. My name is Drew Camron, and I work on some of Unidata's Python tools. Unidata is a UCAR community program, for those of you not familiar, and I work alongside Ryan May, who is also in the chat here to support with any questions for the next hour, but you'll be dealing with my voice for most of the day. So if you're back in your Jupyter Lab interface, I'm working from my own computer, but the steps will be identical if you're working from the ARM Jupyter Hub. We've provided 2 and an extra notebooks today that we'll be working from. First off, we'll be covering an overview of what MetPy is and what it provides. There won't be much interactivity in this notebook. Once I open it, feel free. I'll show you to just run all the cells so they're there for you. Unless you'd prefer to follow along, that's okay too. We'll do that for about the first half hour or so, and then we'll reserve 10 minutes of some walkthrough, and then hopefully 15 or 20 minutes of just playing around trying to make a SKU for this second notebook. If for some reason you aren't able to follow along today, or you aren't in an interactive Jupyter instance, we've also provided a solutions notebook that has everything pre-rendered for you. You can view this also on the ARM Notebooks GitHub page as well. Feel free to look ahead or follow along there if for some reason you won't be working interactively with us today. So let's start in the first notebook, the overview. I'm going to clear out some things to make some room. Like I said, for this one, you don't need to worry about having to keep up. I'd prefer you just get sort of a quick introduction to some of the tools we provide. So if it's more helpful for you, you can come up here to run and hit run all cells so that all you have to worry about is sort of scrolling, following along, and keeping up with what I'm showing off today. Importantly, we've provided this notebook as sort of a reference almost. There's a lot of stuff in here. I do not expect people to immediately become experts in every subject area. Here, this notebook is more put together to show you what MetPy could be useful for your work. Because, as Max touched on, MetPy is a collection of a variety of tools in Python. The entire project is open source. It's built upon or beside a number of other sort of scientific Python packages within the space you might be familiar with, such as NumPy, Pandas, Xarray, etc. And it includes a host of tools from reading data to meteorological specific plots and visualizations, to a host of helpful calculations, interpolations and cross sections, and much more. So I'm going to, again, spend the next 20 or 30 minutes giving a overview of some of those tools, and then you'll have this notebook as sort of a reference paired with our documentation to help you figure out what you might need MetPy for your work. So a couple of important scientific Python packages that are very valuable to have a basic understanding of to benefit from MetPy. Notably Xarray, especially sort of the newest generation of MetPy in the past few years, sort of post MetPy 1.0 if you've been using it for a while. Xarray is very important for all of MetPy's usage and required for some of it. So understanding X-array and the X-array data model and how you interact with it is very important for using MetPy to its fullest. Similarly, if you haven't heard of it, Pint is a unit library in Python where you can define, we'll talk more about this in just a moment, quantities of united values. So for nearly any calculation in MetPy, you will need to define your inputs as something with units so that our calculations know what to do with them. And of course, NumPy, SciPy, Matplotlib for visualization, Pandas for tabular data, etc., are all very valuable to understand before taking advantage of MetPy. So let's go through a quick introduction to all of what MetPy provides, and then we'll dive into sort of a few of the submodules one by one. If you're new to Jupyter Lab, or as a reminder, for those of you who may not have known, you have a helpful little table of contents here on the left of any notebook you're in. And if the markdown has been formatted, you can sort of see headings and navigate the notebook as you go. This may be valuable for referencing again later, or just to keep tabs on where we are as we go through. So let's start off with any other Python project by importing MetPy. That succeeded, thank goodness. I'll take a look, make sure I have MetPy installed, see what version it is. I've got the newest version of MetPy 1.3. And let's say I want to use a function from MetPy's suite of calculations. Let's see if I can reference it here. No, I couldn't find it. So here is a screenshot of our documentation, which we will provide links to, incredibly valuable if you've never browsed it before. MetPy is presented to you as a collection of these sort of mostly separate suites of functionality. So if you're wanting to use, say, MetPy's suite of calculations or MetPy's plotting interfaces or MetPy's file input or file reading suite, you will need to come import those individually. So we have metpy.units, metpy.calc, so on and so forth that we will be relying on over the course of today's workshop. Now that I've imported metpy.calc, you'll see if I check for the documentation of it again, it works this time. Just a little intro. And again, these are the various modules within MetPy we'll be taking a look at today. So let's dive straight in to Metpi.io, which currently is a collection of reading meteorological data and sometimes parsing it into helpful pandas or X-array formats contained within MetPy. So here I'll show off a few really quickly. So I'm going to import MetPy's interface for reading at GEMPAC soundings. If you're not familiar with GEMPAC, it is a collection of meteorological software for reading data and creating visualizations. You may be familiar with some maps created with GEMPAC over the years. We provide the functionality to read files generated by GEMPAC. That was actually a community contribution to our open source project. So let's import these. And first we'll take a look at METARs. If you're not familiar, these are text-based reports from weather observation stations, and MetPy can take these, if you see above, sort of strings of information and parse them into helpful pandas data frames. Also, I touched on before that something very important to MetPy that we'll be relying on later are quantities of information with units attached. MetPy also provides a way to take a pandas data frame, which does not natively support units, and sort of hammer units onto the end of it, creating a sort of dictionary of united information for you. Again, this is just an overview. We'll come back to what units really look like in practice in a little bit. GEMPAC soundings or other formats of GEMPAC data can also be read in using Metpi.io. In this case, we will read it into an X-ray data set. And then finally, though, we of course sort of share this space a little bit with PyArt, which many of you may be familiar with. MetPy does also have interfaces for reading level 2 or level 3 next read data. Okay, let's not worry too much about file input today. Let's instead take a quick look at the vast collection of calculations MetPy offers. We won't dive into any one of them just yet, though we'll present a couple for you to play around with when we take a look at a SKUT. And then we'll talk about using units and how to use those with our calculations. So it's probably not fair for me to pick on any one kind of calculation to show off today because, and I recommend if you are a regular MetPy user, check out our user survey for more information here. People use all of our calculations. People use a variety of them. And so instead, I'll just give you a quick overview of really how many we provide. So let's take a look at metpy.calc. We'll also talk a little bit about some of the interpolation functions really quickly. If you're not familiar with the Python dir syntax, this is sort of showing a directory of functions or modules contained within any sort of name. So here I've imported metpy.calc. Let's take a look at what all is in it. And if I slowly scroll through, there is a lot to keep track of here. There are a lot of potentially helpful functions. It's still going for you and your work. Again, we have loosely categorized these into sort of helpful, maybe niches or categories helpful for your work on our documentation. So if you're trying to discover calculations that are helpful for your work, start there, because there's a lot to just navigate here from the start. But maybe that's helpful for you. Separately, we won't touch on this today, but again, a highlight, you can click on this link here to see the documentation for it, the variety of interpolation tools we provide. Some of these are very sort of just interpolate a profile of data, interpolate maybe to a 2D grid, maybe help me handle some NANDs, and we provide X-array-based cross-section creation, which we won't really show off today, but I have some cool examples I can share with people if there's extra time at the end. Okay, the core thing that we need to cover to make sure you have what you need to play around with SKUTs today are units. And we'll talk a bit about X-array. That is very valuable for using MetPy, period. But we'll focus primarily on units and quantities of units to start. So once again, let's import what we need for this section of the notebook. I'm going to import metpy.calc. I'm going to import numpy to create just some basic arrays to play around with, X-array for later in the notebook. And then importantly, I will be importing units from metpy.units. This module is what will allow me to create quantities or define strings of units, say a meter or a degree Fahrenheit, so on and so forth. So this is what we'll be relying on for our units today. A little note here for people just now exploring MetPy. Because X-array is so core to a variety of MetPy's suite of calculations, if you import anything from MetPy, if you import calculations, if you import plotting, whatever, you will gain access to MetPy's X-array specific functionality that we'll be touching on in just a moment. So you don't need to worry about importing any specific like metpy.xarray or anything. So let's talk about pint or unit quantities. So again, MetPy relies on a scientific Python library called pint to allow us to create, understand, and manipulate data with units attached. So at its core, pint can be used as simply as, if I run this code cell here, creating an array. So here I have a NumPy range from 1 to 5, exclusive. So I have some NumPy array, and then I can multiply it by some declaration of units. You see here there's sort of two main syntaxes we rely on with pints. You can use this sort of dot attribute notation and just type out a string of units. This doesn't support complicated unit strings, but anything sort of simple or one word or one letter or a few letters, you can usually define this way. And you'll see now, if you're using JupyterLab, you get this sort of fancy two-part representation of my quantity of units. You see I have a magnitude, the values themselves, and units attached to the quantity for each of those values in my magnitude. So I have a NumPy array, 1, 2, 3, 4. Each one of those has units of meter. So again, this is just a separate syntax. Using the sort of string notation here allows for more complex units. I think we'll show a few more of those later in the exercise, but you can also define sort of compound units here, like meters per second, so on and so forth. Sometimes, and as you dive into using MetPy regularly, we have some clarification on this in our documentation, a sort of guide for users that I can point people to. But sometimes it's necessary to explicitly define these quantities instead of multiplying by the units, as you've seen above. Usually that's just sort of a hang up on data structures in the space. Say, if you rely on NumPy masked arrays very regularly for your work, they don't play kindly with this sort of multiplication structure. So sometimes it's safer, or even the slightest bit faster, to define your quantities explicitly with this quantity constructor. Within that, your first argument is just, again, the magnitude. So a value, an array of values, so on and so forth. And then the second parameter is your unit string. So if I run this cell, I should get a range of 2468 seconds. Here is sort of showing off defining these compound units. So I'm going to define my velocity as 15 times units meters per second in a single string. I can do just that. Then, importantly, and our calculations rely on this, you can do operations on units. It supports, basically everything you could need, and we'll talk as we move forward on that. It will help you do the sort of unit conversions that may be necessary to get a sensical answer for your calculations, and our calculations do that and need that. So example, of course, you can add quantities together. So I can add time plus time to get to add these arrays on top of each other, maintain seconds. I can multiply. Notice here my units have become meters squared because I multiplied a quantity of meter times a quantity of meter. It changed my units for me. Similarly, of course, I can divide. So if I take my distance and I divide by my time, I can get meters per second. And then finally, a little helper on how Pint can help you if you've done something wrong with your units. So you see here an angry message resulting in a dimensionality error. So Pint is letting me know it can't convert meters to seconds. Note if times have similar, or if units have sort of the same physical dimension, like you see here, brackets length or brackets time, it can convert those for you. So if I did distance in meters minus distance in feet, it would have been okay. But because I tried to perform an operation on quantities with two totally different sort of physical spaces, it's going to let me know. Pint also enables helpful unit conversion helpers. So in this case, if I create my 1 inch quantity, I can use this .to method on it and specify a new unit. And sure enough, it will provide me with my 1 inch quantity and a brand new quantity converted. So why is this important? This is important because science is complicated. As history and engineering has shown many times in the past, having an inconsistent understanding of what unit system you're in, what units you're using, and what you're expecting to get back out of some calculation can be a headache and can make it very hard for us to create helpful calculations if we don't know what unit systems people are working in. So basically, all of MetPy's calculation suite requires you to define your quantities with units to be able to perform the calculation. So in this case, if I want to use MetPy to calculate dew point given a temperature and a relative humidity, then I need to define those. So let's say my temperature was 73.2. 73.2 what? I'm not sure. Just kidding. Units, degrees Fahrenheit. So I know my input temperature is in degrees Fahrenheit. Similarly, relative humidity, I can define here in percent. I could just use a fraction. You know, relative humidity is a bit of a weird one. But if you want, you can explicitly say, no, this isn't, 6,400% humidity. This is 64%. And from that, if I go to metpy.calc.dewPoint from relative humidity, I give it the necessary temperature and relative humidity. Sure enough, I will get an output temperature. And in this case, we've assumed that coming back out, this should be in degrees Celsius. And so if we present that to you, what the resulting units from this calculation are. If this just came back 15.7, you might not be totally sure. Of course, there are some cases where it may just totally make sense or not, but units can really help you explore your data quickly with some confidence once you learn how to interface with them. Okay, we'll kind of breeze through X-ray functionality in MetPy. This is very important, but is also something we tend to sort of teach on its own if we need. But just to make you aware of what MetPy can allow you if you're comfortable with using X-ray, we'll skim through some of these. The important thing is that X-ray supports a accessor interface, basically meaning if you have some X-ray object, you can access a unique suite of methods and properties. You may have usually used .cell for select or a variety of other properties or calculations. If you add .metpy something, you will get a brand new collection of tools that we provide specifically for X-array data arrays and data sets. So I'll show that in just a moment. Remember, I don't have to import anything unique here. If I've imported any MetPy module here, we will get access to the X-array helpers. I'm going to open up an X-array data set, take a quick look at it. You'll see we have some GFS data with some ever so helpfully named time, latitude, vertical levels, multiple vertical levels. We have isobaric 3, isobaric 1. I'm not sure what to do with those. And longitude. I'll get back to why those can be a headache and what we can help out with in just a moment. Familiar, sure. To explore some of the unique things that MetPy provides, we're going to start with just data arrays. So I'm going to pull out one of these variables from this data set. In this case, temperature isobaric, put it in a new variable, take a look at it. Okay, I'll note that now I've pulled out a variable that just has a single vertical coordinate, but programmatically, I may not know what the name of that coordinate is. I may not know if it's isobaric 1, isobaric 3. That can be a headache for getting my work done without having to inspect every single file that comes through my workflow. To help with that, MetPy provides shortcut names for your coordinates in your data. So MetPy will do its best using CF metadata, using just some sort of smart logic within the suite of code to identify more general names for your coordinates of data. MetPy can identify, as you see on this list here, coordinates for time, sort of regardless what they're specifically called, Vertical coordinates, same regardless of the specific names, latitude, longitude, X and Y, so on and so forth. Again, you can access these using the .metpy accessor. So if I want to figure out what my data's time coordinate is without knowing its specific name, I can do my data array temperature .metpy.time, and you'll see it pulled out this time 1 coordinate for me without me specifically knowing that was the name of this coordinate. You can use, I'm going to run this real quick, but skip this cell. You can use these shorthand names if you're familiar with xarrays.cell, where you provided the label of your coordinate and then a value to select on. If you can use the MetPy sort of shorthand names for it to pick out your data coordinates for you without having to specifically know, I need to .sel on, was it isobaric 1 or isobaric 3? I don't know. If I use .metpy.cell, I can just say vertical, and it will go find one of those appropriate isobaric coordinates. And we'll talk a bit more about this. You can select on units. So if your data provide, I don't know, isobaric coordinates in Pascal, but you would like to find the 500 hectopascal level, regardless of what units are coming through as you chew through a bunch of data, here I can specify the units and we will match for you. So if I take my geopotential height data instead of my temperature here, just picked a new variable to work with, .metpy.cell, tell it I'm not sure the name of the vertical coordinate, just give me my vertical coordinate and give it to me on the 500 hectopascal level. And sure enough, it's pulled out geopotential height on a single, if I scroll down, isobaric 3 value of 50,000 pascals. The next important thing that MetPy provides in the X-array space is parsing of coordinate information, or CF metadata. We won't dive too much into this, but basically, if your data are well constructed with attributes that define, say, your grid mapping, so on and so forth, and you're familiar with Cartopy or PyProj, we can read the metadata that defines the projection your data are on, and then we can give you Cartopy and PyProj objects, or sometimes convert around into different CRSs for you. We're not going to dive too much into this today, but just to show off some of these things you can get with these MetPy X-ray helpers. Again, this is mostly a reference for you. This is available in our documentation as well. We also give you control over the units within your X-array datasets and data arrays. If you need it, we can help you pull them out based on the attributes. We can help you convert to and from pint quantities. We can help you convert units of your coordinates. So say, again, if your vertical coordinate is in Pascal and you want to save out to a new file where these coordinates are converted to hectopascal, we can do that with these helpers. Keep these in mind for what may be valuable for your work. Something, that is important to consider for some of MetPy's calculations, and we usually try and tell you if you have to worry about this, is that pint quantities, those array plus unit quantities that we were talking about earlier, don't always play nicely with the X-array data model. They mostly do, but say you may not be able to save them to a file, or it may be difficult for our calculations to pull out the appropriate unit information from just an X-array data object. And so we give you the way to create a pint quantity from the data within your object. So I have this temperature time series that I created above. Don't worry about it. And I just access .metpy.unit array to just get a pint quantity out that I may need for some calculations or plotting. Okay. Also, the last thing to mention here is that some of MetPy's calculation suite either require or become much smarter with X-array data arrays and data sets. So some of our calculations, if you have a data array with appropriate unit information attached, will just work and read your unit information for you, create the appropriate quantities under the hood, do any necessary conversions, and just give you a result back into an X-array data structure. We usually try and tell you if it's required. I think the most notable place that X-array is required to get a calculation done is our cross-section interpolations, as well as we have a few sort of X-array specific LCL calculations, things like that. We usually try and communicate that pretty well if it's required. But for many things, it will just make your life better if you do use it, though it may not be required. Okay, and the last thing we'll talk about in our overview before going to play around a bit is MetPy's collection of meteorological plotting helpers. So you may not be familiar, but many of you will have at least been exposed to the variety of very unique and domain-specific plots and visualizations you can run into in meteorology and atmospheric science. Using matplotlib, MetPy can drastically shorten or lower the headache that it might take to create some of these unique plots. So let's import, I'm going to import Cartopy here for mapping if you're not familiar, as well as a variety of MetPy's plot and units functionality. First thing I'll show off really quick is that MetPy can make station model plots for you. These sort of representations of surface or upper air data that give you like cloud cover, wind speed, temperature, dew point, current weather, maybe pressure or pressure change. We can provide all these symbols or values for you. You can control where to place them around a station model. You can control what they look like, the colors, so on and so forth. To do that, let's really quick open a METAR, one of these representations of surface data. Let's make a quick Cartopy map. And I'm thinning out the data a little bit here. Don't worry too much about the specifics, just so it's not too busy. And then finally, if I come down here, you'll see where we create our station plot. We tell it where they're located on our map, what matplotlib object to reference, what data transformation may be necessary. And then once we have this station plot, we can add things to it like I showed above. So you can add parameters. You sort of specify where in your station model you want this parameter to be. So I'm saying in the northwest, I want my air temperature values and I want them to be in red, so on and so forth. You can also plot symbols. So we give you sky cover fonts, we give you weather fonts that will create these meteorological symbols for, say, cloud cover fractions or the unique array of meteorological symbols you'll see on these station model plots. And of course, barbs or text you might see. If I run this, sure enough, we will get a nice map, ta-da, of these station model plots with our desired parameters. Something else that is helpful for MetPy in exploring your data, exploratory work, or particularly helpful in teaching or for students, is we provide something called a declarative plotting interface, which is just a sort of shortcut to good plots. So basically, if I want to recreate the exact plot I just created by just specifying a sort of list of important information, which our documentation can walk you through what you'll need to specify, but basically I can just tell this interface what data I'm working with, what time it is, what fields I'll be showing on the map, how I will be formatting these station models, what vectors I'm providing for the barbs, so on and so forth. Then I can specify unique information about my map projection, and finally the figure containing it all. Just sort of list this all out, run this, and I get, though a slightly different map, a map of the exact same data with the exact same station models as above. So that's something particularly valuable for, again, sort of very quick exploration of your data, or for teaching people how to explore data in Python. We have a variety of these declarative classes for checking out contours of values, surface data. We even can, I have a link here for plotting geometry, so like shape files or GIS data. We have some really cool examples of showing off, say, convective outlooks from SPC. But the last thing we'll, of course, show off today is MetPy's ability to create the skew-T log-P temperature profile. I'm going to pause here. Again, this reference document has a collection of particularly helpful links and support avenues for using MetPy. So keep this on hand, play around with this, take a look, and see how it might be helpful for your own work. So let's take a step out of this. I'm going to close this notebook. And let's make a skew-T. So I'm going to open this notebook. Remember, if for some reason you can't follow along today, or earlier in the week we were having some data access issues, if you run into that today, let me know, and I will help you use our solutions to sort of short circuit that and fix the issues. But regardless, if for whatever reason, please feel free to follow along with the solutions as well. Because for this part, we will play around together and do some exercises in making a skew-T. So for this, don't worry about necessarily needing to go learn new syntax. I will present to you everything you need to make a skew-T, and then just ask you to do a few extra steps. And then at the end, we will have plenty of time to explore adding totally new things, or trying out creating a skew-T on new data, whatever. So for this example, let's first grab a profile. Let's grab a sounding to plot on a skew-T. Another tool that we have created and we maintain in Unidata is called Siphon. It's primarily used for accessing data on a Threads data server, another one of Unidata's products. However, we also give you some shortcuts to a few meteorological data collections on the internet. One of those, if I import these, is the Wyoming Weather Web sounding site. There are links to a few of the different places we can give you data from. And of course, check out the Siphon documentation if this is helpful for your work, but I'm not going to go too much into the specifics of Siphon today. All you need to know is we're going to create a request for Siphon to get a certain sounding from the Wyoming Weather Web. So here I've created a time. This is, I will be getting a sounding from 1999, May the 3rd at 12Z. For those of you not familiar, that is the Moore, Oklahoma 1999 EF5. Then I'll be specifying the station. You can use the sort of K 3-letter iCow identifier. That's what you may often see in some of our examples, or this 5-digit ID. These are for the same station, but this is from an Oklahoma sounding on the day. And then finally, we're going to request the data given that time and station and take a look at the data frame we get back. So this is pretty straightforward. We have a data frame of pressures going down in value, ascending in the atmosphere, and other important quantities to go along with them. Importantly, Siphon, this is not something that you'll just naturally find in Pandas. Siphon sort of hammers on unit information to the sounding data frame so that MetPy can understand it. So here I can take a look at this units attribute that is not always there. That is something that Siphon puts on to these data frames for you. Otherwise, you may need to create this for parsing this data frame into a collection of united quantities. So I'm going to do that now with this Pandas data frame to unit arrays. This is just a pretty straightforward tool that takes a data frame, with that unit information hammered onto it, and provides back to you a Python dictionary of individual pint quantities. So those arrays with units for each column that was in our data frame. So as we scroll through, you see I have a dictionary. It's got a pressure key with this array with units, height with array with units, so on and so forth. And we'll be relying on this for creating our sounding. So I'll skim through this. If you're not familiar with Python's dictionary notation, we'll be using the sort of bracket quotes to access those individual quantities using their key. So I have a sounding dictionary, and I want the pressure quantity out of it. I'm going to use that notation, and sure enough, you'll now see the nifty pint magnitude in units Jupyter representation of this quantity. So we have our data. We have our information with units attached for us. Let's check out metpi.plots.sqt. So sort of similar to our station model that I showed earlier, we'll first create a sqt object. I'm going to do that by first making a matplotlib figure, specify how big I want it to be. You don't have to specify anything here, but it's usually a good place to start. And then I will tell sqt the figure I'll be working with and create this new skew object. We don't see much so far. It is nice to see that it worked. I now have a sort of canvas to work on. I have this sort of skewed axes within my figure to plot some data on. Within these skewed axes, I have access to most or much of the sort of usual matplotlib plotting syntax you might be used to. So in this case, I'm going to plot a line on my skewed axes. It will have coordinates of pressure up the side of the axes, temperature, determining where on the sounding our temperature values fall, and then I'm going to provide it with a color. In this case, if you're not familiar, this tab is just specifying a certain matplotlib color table. The tab 10, I believe, collection of colors. They tend to be a little bit more readable on a white screen. And we'll take another look at the figure. Sure enough, we have a brand new line. This is our temperature line plotted on our skewed axes. Recall, if you need to plot a new line on this skewed plot, come back and check out skew.plot. Something that we may not necessarily rely on, but just to show off, you can use Matplotlib's AXV line or AXH line to draw straight lines on your plot. This might be useful to denote, say, an isotherm or a level of pressure that's important for you. So if I show that real quick, I drew the 0 degrees Celsius line, straight line on my skewed axes. Note, of course, it's not actually a vertical line because everything is skewed. Of course, like any other matplotlib plot, you can set the x and y limits with the set xlim and set ylim methods. Here we sort of shrink it, make it a little more zoomed in on our profile. Then within a sqt object, we also give you a variety of specific plotting tools. So in this case, I provide for you, I'm going to back this out, the plot dry adiabats function, which will highlight a sort of smart collection of default dry adiabats in the background of your plot. You see also we have mixing lines or moist adiabats you can come highlight on your sqt. But let's take a look at dry adiabats, run this function real quick, take another look at the figure, and sure enough, you now see these lines in the background denoting some helpful default dry adiabatic lines. You can explore everything available within this with that same Python dir notation, or if you're in Jupyter, again, check out the tab completion. So if I type out my object, hit dot, hit tab, I see the list of properties or functions available that I can sort of summon from that. So let's do a quick calculation and let's plot it on our SKU-T. I've decided from the documentation I want to plot the parcel's profile. So if I have a parcel at the surface and I lift it, how will its temperature change with height? So will it lift dry adiabatically, moist adiabatically if it hits the dew point, so on and so forth. I want MetPy to calculate that for me and provide me the temperature trace of a parcel lifted from the surface. So I'm going to check the documentation of that function. I'm going to see that I need my pressure from my sounding, my temperature from my sounding, or in this case, the pressure of my sounding, so bottom to top, the starting temperature of where my parcel begins, and the starting dew point. And then it will go through and calculate the temperature throughout the entire profile. I'm going to cram the output of this back into my sounding dictionary just to keep things in one place. So let's create a new key in the dictionary called profile. And from that, that will be the output of metpy.calc parcel profile. I give it the pressure of my sounding. I give it the starting temperature of my sounding, the starting dew point of my sounding. I'm going to run that. I'm going to insert a new cell real quick just to take a look at that. Let's take a look at our profile quantity. Sure enough, we have something here that it didn't yell at me. I didn't get any errors. Units of Kelvin, okay. Let's take a look and see what that looks like. So now, following the same syntax as above, let's plot this profile on our SKU-T. So I give it the pressure coordinate, what pressures to plot this trace. I'm going to color this one just solid black. Let's take a new look. Sure enough, there is our parcel profile. Note this is kind of cut off because of my X limits that I set earlier. I'm going to make y'all fix that for me. I can't really tell where this starts or what's going on here in the bottom corner, but we'll worry about that in a moment. The last thing to show off is that without calculating anything, though I suggest that if we had some time, we explore calculating it, we can shade CAPE, which, if you're not familiar, are any regions on this profile where the parcel is warmer than its environment, indicating instability, indicating that that parcel will continue to rise as long as it's warmer than its environment. I can have my SKU-T plot shade in this CAPE for me and show me the regions where my parcel is warmer than my environmental profile. And sure enough, we see for this entire region from about 700 millibars to about 250 millibars or so, my parcel is warmer than the entire environment it's within, indicating a pretty deep region of instability. So I've shown off everything you need to expand on this SKU-T to make it better, to add some more meaningful information, and to make it more presentable. And I think we will take the remainder of our time. I know we may not have as much time as I'd hoped, but I'll take the remainder of our time to play around with this and give people an opportunity to share what they come up with and ask questions along the way. So I've given this exercise here for you to walk through now if you're able, or else on your own time, and feel free to reach out to us. But basically, using the documentation if you need it. Otherwise, everything you need should be contained in the code cells we just walked through. Take our existing SKU, our SKU-T object. If I take a look at that, take this existing SKU-T, plot the dew point, preferably in green or blue or whatever color stands out better to you, on this SKU-T from our sounding dictionary. Add some moist adiabats and mixing ratio lines to the background. You can specify these by hand if you'd like. Otherwise, just let MetPy figure out where they're helpful. Help me fix the range of our SKU-T that's useful and pick a new X and Y limit to make this profile more visible. And then, similar to the shade CAPE function, see if you can shade any SIN or convective inhibition present on our profile as well. If you've already played around with this, or if you have some extra time, I've also prompted some interesting bonus considerations that we can explore in the last few minutes. SKUTs allow you to plot wind barbs along the side if you have U and V winds, which we do. We can also actually calculate CAPE and get a number for that entire shaded region, see what that actually looks like. Or we can take a look at some new data. So I'm going to step back here. I think I'll stop sharing my screen for the moment and share it again if I have any questions. But so I can get to the chat, I'll stop sharing my screen. Okay. So it looks like we only have about 5 minutes here at the end. If you get a chance to expand on this SKUT, if you're comfortable with sharing your screen, that might be the easiest way to show it off. Otherwise, I can provide a place for you to sort of give us a gallery of some cool SKUTs you make here at the end of the day.
Thanks, Drew. There is a question here, and this might be more for Arm or Monica if Monica's on, or for Max or Monica if Monica's on. But does tab completion work on this Arm Jupyter Hub? And I will say I didn't quite get that working either. So is there an extension you need?
Nope. If the code is imported, so you do have to make sure that you've run the cells that imports the code. It should work in any install of Jupyter. There are certain configurations to Jupyter that may change the tab completer here. And so if you're running into that, it's a safe bet to check the documentation or use that dir function to just get a list of what's available. You just also end up with a lot of extra things that might not be helpful if you get the directory. I will, to make sure that people have an opportunity to sort of chew on the SKUT exercise here, I'm going to respond to some of these questions in the chat instead of out loud.
Okay.
But as we get towards the end, I can also speak up.
Okay.
Yeah, I saw that there was another question from Ken. Is there a way to get the correct x-axis temperature value that will correctly show all of the plotted line programmatically? For example, what if the temperature line curves to the right, high aloft? Then you provide an example.
So I can answer these questions out loud, I guess, since we don't have too much time left. Fan May, the MetPy should be able to plot any sort of profile as long as you have a vertical coordinate and temperature value to plot. If you run into any issues using MetPy with your particular profiles, I'm not familiar necessarily with the specifics of ARM sounding data. If you have any issues there, please use the support links in the first notebook to reach out to us and let us know, and we'll try and make sure it does work. Ken, so yes, what Ryan said, as long as you can get it into an appropriate NumPy array or pint quantity, then you should be good to go. Ken, the SKUT will try to adjust to sensible limits automatically. Yeah, if you're trying to create multiple soundings, generally you can get away with just not specifying the limits of the plot and having it try and find a good sensible limit for you, but that may be difficult to do with without totally taking a look to make sure yourself.
Okay, any other questions here? We got about a minute left. Okay. It does look like the conversation is still going on in the chat here. I definitely thank you, Drew and Ryan. There's a question there quick on not sure where to find the files.
These are in the repository that you're accessing via the ARM Jupyter Hub, or if you've cloned the repository onto your own computer. So they are in the tutorials data folder. And within that directory are all of the data that were being used for these examples.
Okay, and then just last question here. Can someone delete a profile in this QT plot after they've plotted it?
Ryan may have an answer to if that is itself true. Generally, with recreating plots in Python, it may be more straightforward to sort of modify your code to create the plot without it to begin with.